Okay, so recursion, we're going to do this by example. I'm just going to jump into a recursive example to start explaining it, and then I'll start talking about the concept after that. So recursion, the one-liner, what is recursion? It's a method that calls itself. Methods, because we're working in Scala, a function that calls itself is also a recursive function. We're going to see recursive methods, methods that call themselves. Don't worry if you can't read this text. You're not supposed to be able to read it. I'll fill this in as I talk about each section, and by the end you'll be able to see the whole example. I had it completely wiped out so you couldn't read it at all. I decided to make it somewhat readable, but don't panic if you can't read that. You're not supposed to. So it's a method that calls itself, but I want to expand the implications of that and how that works. How do we have a method call itself when we aren't even finished writing a method yet? We're not even finished writing a method yet. We're going to start calling that method inside itself. This is one of them topics that it's confusing. There's no getting around that. It's a confusing topic. At first, it's going to look like it just works by magic. If you don't really understand how recursion works right away, do not panic. It's one of them topics that can take years to understand and years to really see what's going on with it. And I will note, this is a review week for Learning Objective 1. I'm using recursion as an example to show you more memory diagrams. I can't start LO2 concepts, and I can't show you new LO1 topics because some of you all took the interview and quiz yesterday. It wouldn't be fair to introduce new stuff and then ask it on the quiz and interview. I just can't do that. So I'm going to use recursion as a way to talk about more memory diagrams. And then later in the semester, specifically when we talk about trees and linked lists, I'll bring it back a little bit too. Trees and linked lists, we're going to start working with recursion a bit more. So I just want to give you a flavor, a little taste of the topic now. So the example we're going to use is a method called sum to n, which is going to sum the values from 0 to n. I have 1 to n on the slide, but technically if 0 is an input, it wouldn't be 1 to 0. So 0 to n, sum the values. We're going to call it with the argument 3. And I would expect the return value to be 6. 1 plus 2 plus 3 should be 6. Now, before you say anything, you could do this with a loop, no problem. If I gave this as a task on a project, you'd be like, this is easy. You're going to start your accumulator variable like we did in 115. You're going to loop over the values 1, 2, literally write 1 to n in Scala to iterate the values 1 to n inclusive of the endpoint. And then sum up your accumulator variable, which you initialize at 0, and then return the accumulator at the end of the loop. Like you could definitely do that with a loop. And in this case, it's about the same amount of work to do this with a loop as it is for recursion. So I just want to throw that out there. I'm going to solve this with recursion to show you your first recursive example. Yes, I know you could solve this, since like halfway through 115, you would be able to solve this no problem. Maybe earlier than that. So I just want to throw that out there, make sure we're clear on that. So when writing a recursive example, we're going to write it in 2 parts. One part, highlighted right now that we just added in. I got to lower this. That I just added in is what we're going to call the base case. The base case is going to be a trivial input-output behavior where I just trivially know the answer for a specific input or a specific set of inputs. For this one, I'm going to say if you give me the value 0 and I'm asked to sum the values from 0 to 0, I'm just going to return 0. Like I know the answer to that one. It's a really easy input to compute the answer for, and we're just going to hard code that answer. You give me 0, I'll give you 0 right back. Sum the values from 0 to 0 at 0. Done. I'm also going to put a less than here, just in case somebody gets smart and gives me a negative number and says sum the values from 0 to negative 3. I'm just going to give them back 0. I'm going to say I don't play that game. Negative numbers are going to sum to 0. That just takes care of the special cases of negative numbers. So I'm going to say n less than or equal to 0. I'm just going to return 0. Very important to have this base case, but it's going to be very simple to code as well. Give me a simple input, I'm going to give you a simple output. If the base condition is not true, so if n is not 0 or negative, then we're going to hit our else statement. So the top level of most recursive methods are going to have this conditional. If we're looking at a base case, return the solution to the base case. Else, we're going to enter our recursive case. Now the recursive case is where we're going to make our recursive call, which is where the magic happens here. So we have sum to n, the method that we're writing. The method we're currently writing, we haven't even finished writing this method yet. And we're going to call that method. Sum to n is going to call itself. Whenever a method calls itself, or a function, we call that a recursive method, and we're playing with recursion at that point. A method that calls itself is a recursive method. So as soon as we have that recursive call there, this method calling itself, that's a recursive call. We got ourselves a recursive method. We know we're working with recursion. This is where the confusion starts too. Or I shouldn't say confusion, but it just takes a little bit to really wrap your head around recursion. It can take years, like I said. It takes a long time. Which is why we're starting with about a simple example as I can get, to give you an easy sample into recursion for your first example. When we write our recursive call, there's an important property it has to have. It has to get closer to the base case. So our base case is 0. We wiped out the possibility of any negative numbers getting into our recursive case. So we know we have a positive integer, and our base case is 0. If I subtract from n, I'm going to get closer to my base case. So no matter what n is, if we hit the recursive step, it's a positive integer, we're going to subtract 1, which is going to get us closer to 0. And we're going to make the minimal step possible. This is what I like to do in my recursion. I think generally a good idea. We're going to take the smallest step possible that's closer to the base case. So if I have a positive integer, the smallest step I can do to get closer to 0 is subtracting 1. If I just subtract 1, smallest step I can take to get closer to the base case. So that's going to be my recursive call. I don't know how that's going to fit into the puzzle of this whole method yet, but that's going to be my recursive call. One small step closer to the base case. Is it still? I turned it down, but it should still be on. I hope anyway. Yeah. And then students hate it when I say this sometimes anyway, but we're just going to assume that the recursive call returns the right result. Just going to assume. Now don't worry, students don't like it when I say that first, but don't worry, I will explain that. Right now we're just going to pretend it's magic. I will explain why that assumption is going to be correct and how, but for now we're just going to assume that sum to n of n minus 1 does return the sum of the values from 0 to n minus 1. Just going to assume it's correct. So on the input 3, we make this recursive call, sum to n of 2. And we're just going to assume that that returns 3. 1 plus 2. We're going to assume that returns 3, and then build the rest of our logic around that assumption. If this returns the sum of all the values from 0 to n minus 1, and my task is to return the sum of all the values from 0 to n, all I've got to do is slap a plus n on that, and I'm done. So if my assumption is correct, that sum to n of n minus 1 returns 1 plus 2 plus 3 plus 4 plus all the way up to n minus 1, and I add n plus to all that, I have the values from 0 to n, the sum of all those values. So as long as this does, in fact, do what it's supposed to do, I'm going to plus n and return. And as long as we have faith in recursion, everything works, and we're done. This is another property of recursive methods. It looks like we didn't really do anything. All we did was add n, effectively. That's like the only line that really does anything, is the plus n. But I promise you this method does do what it's supposed to do. This works. Everything's fine with it. It actually will return 6 if you run this program. It's in the repo. By the way, I pushed it to the repo this morning, so if you poll, you'll get this example in the LO1 program execution and then a recursion directory, recursion package. It does do what it's supposed to do, but it looks like we didn't do anything. How the hell does this do what it's supposed to do? So with our assumption is going to be true when we call that with the base case. So when sum to n of n minus 1, if n is 1 and this is sum to n of 0, well, we know that's going to be true because it's our base case. And then our base case is going to start off this whole process of calculating the correct solutions. If I have sum to n of 1, the base case, sum to n of 0, that's true, it's going to return 0. I'm going to add 1 to it, and sum to n of 1 is going to return the correct answer. It's going to return 1. Sum to n of 2 is going to get that 1, add 2 to it, and return 3, and return the correct answer. And it's going to go all the way up to whatever n we called initially. So our assumption will end up being right if we set up all the pieces of the puzzle properly, which are a trivial input-output base case, a recursive call that gets closer to the base case, and our logic, sound logic built around the premise that our recursive call will return the correct result. All right, any questions yet before we memory diagram this? So my assumption is that it still looks like magic at this point. I want to break it down in a big memory diagram, but before we get into that, any questions? Yeah. Yeah. Mm-hmm. But recursion won't be on the quiz this week, so you don't have to worry about it in that sense. But yeah, where the return value goes is the big question for that. And I'll show, we have special notation for that. Where did I learn alchemy? Full Metal Alchemist. All right, so let's take a look at this. So we start off simple enough. It's a method call. We know how to put method calls on the stack. This should be very familiar to us right now. But I want to say right off the bat, I'm going to start doing things in my slides, in my memory diagrams on my slides that you can't quite do on pen and paper. Things to tidy up the slides a bit. You'll see what I mean when we have a method call return. When a method call returns, I'm going to gray out that stack frame instead of crossing it out. For the first few memory diagrams I show you, I like to show them exactly how you're going to write them on paper. I don't want to use any tricks that I can only use on the slides. But now that you know the notation, you know to cross things out, for example, I'm going to stop doing that on my slides just so you can read things. You already saw in my last example that my crossing out covered up some of the information. I want my memory diagrams on the slides to have all the information, just because I have more tools in my toolbox since I get to use software to write these things. So just a heads up on that. All right, so we start with a stack frame, n equals 3, sum to n. We have our main stack frame with the value for our return value, no actual value on the stack, and we're going to draw an arrow to where this stack frame is going to return, plus the name of the method of this stack frame. Oh, that's old news. Conditional is false, so we're going to go into our else. And since this code block, since there are no variables declared inside this code block, we're not going to draw the dashed box for this else block. It's optional. You can draw the empty dashed box if you want. Since there's going to be nothing in it, I'm going to opt to not draw it, again, for reducing clutter and increasing readability of the memory diagram. So I'm not drawing my dashed box, and then I'm going to have a stack frame for this method call. Our stack frames never go inside each other. A new stack frame will always go at the next available space in the stack outside of any other stack frame. They are completely independent of each other, and we denote that by drawing them completely separate of each other. We wouldn't draw a stack frame inside a stack frame ever. That is a distortion of what's actually happening in memory. In memory, they are two completely separate spaces on the stack, separated physically on our RAM sticks. We're going to denote that accurately in our memory diagrams by not showing a stack frame inside of another stack frame. So our new stack frame goes below. And our special notation for recursion, we always draw this arrow to where the return value is going into a variable. But the way I have this set up, I'm not storing the result of this method in a variable. I'm using that to be the return value for a recursive method. For that, we draw our return arrow just to the stack frame that made the recursive call. Without recursion, for memory diagram examples, I'll usually store this in a variable and then do it that way. For recursion, that's just a lot of extra clutter. We just draw the arrow to the stack frame that made the recursive call. And notice we have two stack frames with the same method name. We're calling the same method multiple times. They're both on the stack. We just write the same method name both times. This method call, this stack frame with n equals 2 is going to run. Condition still false. So we hit the recursive call again. Slap another frame on that stack. So we're going to reach another method call. That's another stack frame, just like any other method calls. On Monday, we saw an example where we had a method call another method, put another stack frame on the stack. Same thing is happening here, except we're getting more stack frames, and those stack frames happen to be for the same method call. In this stack frame, we have n equals 1. Condition is false. Go to the else block and make another recursive call. Just keep repeating the process. This process repeats, and we keep adding frames to the stack until we reach the base case, which we're about to do here. We have a stack frame where n equals 0. We're about to hit that base case, and at this point in memory, we have 5 frames on the stack, all 4 of them just waiting for a recursive call to return. This stack frame with n equals 1 is sitting right here waiting for this sum to n of 0 to return. This stack frame is waiting for a sum to n of 1 to return. This stack frame is waiting for sum to n of 2 to return. And the main stack frame is waiting for sum to n of 3 to return. So they're all just sitting there waiting for these return values so they can finish up what they need to do. But they can't do anything until we start hitting this base case, which is going to return 0. That base case is going to return, that stack frame is removed from the stack, and we return control to the next stack frame on the stack. So the stack frame returns. This is where you would cross it out. In my slides, I'm going to start graying them out like this for readability. This stack frame returns 0 to this stack frame where n equals 1, which was sitting right here waiting. It waited. This returned 0. And now it can continue its execution. So this, what's highlighted, resolved to 0. We're going to add n in the currently active stack frame. We look at down the stack. The bottom one visually that hasn't been removed from memory is this one right here, n equals 1. So we have 1 plus 0, and we're going to return 1. So thinking about our assumption, we just made a call sum to n of 0. That was the base case, so our assumption was true. This stack frame got 0, returned 0. Everything's fine with that. It's the base case. Of course it's going to be right. Of course our assumption is right for the base case. But that kicks off this process where now we have sum to n of 0 return the correct answer. We're going to add 1 to that and return the sum of 0 to 1, which is just 1. We're going to return that to this stack frame where n equals 2. This, our assumption was correct. This did return 1 like we expect. And then we're going to add 2 to it. So we got the sum to n of n minus 1. We're going to add 2 and return 3. Well, sum to n of 2 is returning 3. That's what we expected there. Our assumption's still correct. And we're just going to keep going down the process. We could call, if in main we said sum to n of 100, this process would go 100 stack frames deep and then 100 stack frames back up, all computing the correct result. So the work is actually being done by creating multiple stack frames. And each stack frame just does one piece of work, the only work that we coded, this plus n. That's all any stack frame is doing, I guess besides the base case, which just returns 0. It's the only work, but we're going to get n stack frames with different values for the parameter n, and they're all going to add just their value. So this returns 0, this stack frame added 1, this stack frame added 2, this stack frame is adding 3, and then we get our result of 6 by taking advantage of multiple stack frames. I guess n plus 1 stack frames. So we got 4 stack frames to do our addition. 1 to return the base case, and 1 each to add 1, to add 2, to add 3, and then return our 6. You can, if you want to draw your empty code blocks, you can. Wouldn't the n equals 3 go in code block for that block? Would it be the same stack frame? We didn't declare any variables inside the stack frames. The only variables we have in these stack frames is the parameter, which is declared outside of the code blocks. So we wouldn't have to draw our code blocks. If we did like var result equals sum to n of n minus 1, and then n plus result on the next line, then we would have a variable declared in a code block. We'd put that in a dash box inside our stack frame. And our assumption was right for all these examples. We can be reasonably assured that it's going to be right for any inputs. So that's the magic of recursion. And don't forget your print values. Silly thing to forget on the quiz, don't forget those print values. Yes? Yes. So I'm just graying them out in my slides. So from here onward, I'm going to gray them out for readability in the slides. For your quizzes, you would still be crossing them out. But just to keep my slides cleaner, when we get to learning objective 2, these memory diagrams get big. They get huge. Not like huge, but big for a slide. And I got a lot of information to cram in there. I need it as readable as possible. So I'm going to start switching my syntax. But the first few, I wanted to show you the way that you'll do it on the quizzes. So nobody's asking me, how on a quiz do I gray something out? Should I shade it all in or something? You know, I just want to show you how you'll do it on the quizzes first. Yeah? Can you explain why it's not 16? Yeah, so sum to n of 3. This stack frame returned 6 to the main method. We stored that in result. And then when we print result to the screen, result is 6. So we get 6 printed to the screen. How could I study stack frames? That's an excellent question. I'm glad you asked. Why couldn't we cross out the 2? I will answer that question, by the way. Why can't we cross out the 2 to replace with 3 if we are adding? Why couldn't we cross out the 2, like right here? Cross out the 2 and... Oh, my eye. So we wouldn't cross out the 2. The value in n isn't changing. We actually have 4 different variables named n on the stack, all in different stack frames. So we would never cross out those variables. In fact, in Scala, any parameters are declared as vals. You can't reassign the value of a parameter. So we wouldn't be able to cross those out. Unless you're asking for our memory diagram, could we use that as a shortcut, kind of like we did with the vals inside a loop? And we don't because we want to make sure we show these as separate stack frames. We want to visually know that 4 stack frames were added to the stack. Any other questions on this one? It's our first recursive example, so I want to make sure I go nice and slow here. Recursion takes a while to absorb. Maybe this example, you're probably not feeling too overwhelmed that it's not too many moving pieces, but just seeing that code and how much we're leveraging the stack and stack frames is it takes a while to see. Like this little unassuming n plus and then a recursive call is actually going to get all these stack frames added to the stack. We leverage the stack, and each stack frame does a little bit of work. That's the power of recursion. That's what makes recursion such a powerful concept. All right, let's modify this code just a little bit. So it was, actually let me cue this up a little better. So when we got to the base case, this is a very important part of our program. We kept adding stack frames to the stack until we hit our base case. Our base case did not make another recursive call, it returned, and that's where we can start going back up the recursion and start returning from each stack frame and going back the other way. So we're adding a bunch of stack frames. Once we hit the base case, it returns, and then all the other stack frames get to return after doing their computation. So let's modify this code just a little bit in a pretty major way. I'm going to remove that base case. What happens if we never do hit that base case? What's going to happen with our recursion? So let's go right back to where we were when we first hit the base case, where now n equals 0 is not going to hit the base case because it doesn't exist. And we're just going to keep adding frames to the stack. Every single call of sum to n makes another call of sum to n. When will this stop? It's just going to keep making calls. When does this stop if we don't have a base case? Well, it stops when things break. So our stack only has a limited amount of memory. There's a finite amount of space. We start our program. Our program says, hey, JVM, I need some space. The JVM says, hey, operating system, I need some space. We get a designated space for our stack. Once we fill that up, we're done. We don't get more. That doesn't change. So once we fill up our stack, we're going to get that Stack Overflow error, the namesake of our favorite website, and then things crash, program's over, nothing works after that. You fill up the stack. Now, the stack space is quite large. Unless you're writing infinite recursion, it's pretty hard to fill up the stack. So don't panic. Don't think. If you're like 5 nested method calls deep when you're writing some code, don't worry about running out of stack space. You have tons of stack space. You can put thousands of method calls on there. But once you start having infinite recursion, or recursion, like if I say sum to n of 1 billion, you're going to start filling up that stack space and run out of space and get the Stack Overflow error. So we need that base case. That base case is very important, and we have to always hit that base case. So to write my CS degree, to write a base case, so to write a recursive method, we're going to start with a base case. I'll preface this by, this is the way I like to write recursive methods. If something else works for you, go for it. But the way I like to approach a recursive method, I'm going to start with the base case. I get some problem, say I have to sort a list. I'm going to think of a base case that's as simple as possible. I don't want to make it any more complicated than it has to be. So if I have to sort a list, well, what list can I sort really easily? Well, how about an empty list? If you give me an empty list, I'm going to sort that just by returning an empty list. What if you give me a list with one element in it? You give me one element in a list and ask me to sort it, and I'm just going to return it. It's already sorted. I ain't got to do anything if there's only one element. It's in order. It's in sorted order. I don't even care what order you're asking about, increasing, decreasing. I don't care. I'm just returning that thing. Those are my base cases if I'm trying to sort. And we'll see a sorting example with merge sort on Friday. I'm just going to return that thing. I like to keep my base cases as simple as possible. I have seen merge sort. I think it was an example that I was in lecture as a student and the professor was showing it. And they had a base case of size 2 or less. And they said, if I have an input of size 2, compare the elements. If A less than B, return a list with A and A then B, else B then A. And it's just overcomplicated. You don't have to overcomplicate that. That's just more opportunities for you to mistype something, more opportunities to introduce bugs. I don't want any bugs in my base cases. As simple as possible. Common base case inputs, empty list, empty string, empty map, 0, 1. Anything that's going to be absolutely trivial to compute. Sorting a list of size 1. I can compute that. I don't even have to think about it. We're going to have a conditional. We're going to check, is this the base case? Is the input one of my base cases? If so, return the base case solution. Else, we're going to enter the recursive step. If I'm in the recursive step, to write the recursive step, I know I'm going to make a recursive call at some point. I like starting with the recursive call. I'm going to write a recursive call that gets me some small amount closer to the base case. If I'm sorting a list, which we'll actually see something different on Friday with merge sort, but if I'm sorting a list, if I can just get, or working with a list, I'll say, if the input is a list, can I handle one element of that list? Can I process one element and then make a recursive call with the rest of the list? That's going to get me closer to my base case, assuming my base case is an empty list or a list of size 1. That's going to get me closer to that. And then I just got one single element to process. Then I'm going to assume that the recursive call just does what it's supposed to do. I'm going to assume that it took the rest of that list and just handled it exactly what my method is supposed to do if I were done writing it. As though I were done writing it and it was absolutely perfect. Just going to assume that it's going to work, because it will work if I follow these steps. With that assumption, I'm going to build the rest of the logic of my program. I'm going to say, okay, if that returned the correct result, and I got this one element to process, I just got to process that, combine it with the result that I got from my recursive call, and then return that. For our sum to n, we just assume that sum to n of n minus 1 return the correct value. And now all I have to process is the value n. I have to add n to it, and then return that. So assume that your recursive call is correct. Make sure it gets closer to the base case, and then build your logic of your recursive step around that. So if you have all those ingredients, the recursion is just going to work. It's all going to work just fine. If you don't get closer to your base case, that's where you're going to have infinite recursion and Stack Overflow. I completely removed the base case in the example. But if you have a base case that you're never reaching as well, then you're also going to have infinite recursion. You're going to put infinite stack frames on the stack, and your program is going to crash when you run out of memory. Run out of stack space. So a base case, trivial input-output, recursive step that makes a recursive call that gets closer to your base case. Assume that recursive call returns the correct answer, and build your logic around that assumption. If you have those 3 steps, those 3 ingredients, mix them into your recursive method, your assumption will end up being true, because it's trivially true for the base case input, and then your logic kicks in after that and makes all the other recursive calls also true. My 3 ingredients for successful recursion. I have slides for the anagrams example. I wanted them just to show the anagram stuff. I'm not going to show them in lecture, but if you want to look at them, if you're curious, they're there. I don't expect you to understand the anagrams code if you are looking at those slides. I don't expect you to understand all of that. There's some things that I don't even cover in the class anymore, some functional programming concepts. So it's just there for if you're really curious how that works. Some of the functional programming stuff, like you might not understand that anagrams code by the end of the semester. I've shown a lot of weird stuff with that one. So it's fine if you don't go through those slides. I'm not going to. But I do want to get some more debugger in here. So we're going to take that code that we saw in the slides, and I want to run this in the debugger and show you how to run the debugger. So the question is, how do I, which of course I plan to do this anyway, but the question of how do I practice memory diagrams? The debugger is one of your best ways, or as I said, I think that was in this lecture right last time, if you draw a memory diagram, if you pull up like any of the example code or write some code of your own and write the memory diagram and then bring that code and memory diagram to office hours, myself or any TA would be absolutely thrilled to go through it with you and check it with you, basically grade that memory diagram. We'd absolutely be thrilled to do that. Because we don't get questions like that. I don't think I've ever gotten a question like that, unfortunately. I'd be so happy to see somebody doing that. But it is what it is. So if you don't want to go to office hours and have us walk through, this is how I would generate memory diagram solutions, I guess. So I'm going to go into IntelliJ. I'm going to set a breakpoint. For now, we're going to start with the first line of main for my lecture examples. For your homework, you might not want to start at the first line of main. You can set your breakpoint like inside a conditional. Maybe I only want to worry about when the base case is hit. I'll set a breakpoint there and then start my debugging there. Especially for your homework, you're iterating over a file with over 130,000 lines in it. You're not going to start at the beginning of main or the beginning of your test cases and click through 130,000 lines. You're just not going to do that. So what you can do is set a breakpoint inside one of your conditionals in your loop. You have some conditional which says if the country code is the country code I'm looking for and the region code is the region code that I'm looking for, then do this code. Put your breakpoint inside that block, inside that conditional, and then you can see what's happening exactly when your code is doing, processing a city that you actually care about. Then you're only clicking through a few cities to see to see your code in action instead of trying to find the spot in this loop over this file that you're interested in. So I'm going to set my breakpoint at the beginning of main for this example, run this in the debugger. And at first I'm going to see just the main stack frame with a few things that we don't worry about in this course and that we don't put on our memory diagrams once it compiles and all that. This and args, neither of these we worry about. You'll see those in your debugger. We don't put those on our memory diagram. They are on the stack, but we just we don't worry about those. That's something that we will worry about in LO2, but I'll talk about that when we get there. For now, we don't mess around with that. And args, which we just don't use in 116. So we're not going to clutter up our memory diagrams with it. But you will see those in the debugger. They are there on the stack. And I'm going to use this step into to step through my code one line at a time and enter any step into, the reason it's called that, into any method that's called. So I'm going to click this. We have a method call, and it's going to go into that method call. Oh yeah, when I'm setting these, this is what's called a breakpoint. The debugger is going to run until it hits a breakpoint, and it will always stop at a breakpoint and then show this display. If I don't have any breakpoints and I run the debugger, I'll get rid of that breakpoint and then click rerun debugger. It just won't really do anything useful. So compiling, and then it just runs. It's just the same as hitting run. But if I set a breakpoint, let's set a different breakpoint just to show this off. I'll set a breakpoint inside my sum to n and run the debugger. Your code is going to execute until it hits a breakpoint, and then it's going to stop and show me everything in memory at that point. So we got to this breakpoint. We have a stack frame, a new stack frame on the stack, sum to n. It's currently on line 6, and it has a value of n equals 3. It also has this, again, not worrying about that quite yet. It has a value n, the parameter, and it's equal to 3. It's going to execute this conditional. Conditional is false, goes into the else. Oh, I want this more than the code. We've been looking at the code for a while. Going to make a recursive call. N is 3, so it's going to make a recursive call sum to n of 2. And we can see we have another stack frame on the stack. We have our main stack frame, which is sitting at line 14, waiting for sum to n of 3 to return. We have sum to n on line 9, with an n equal to 3. And we have a sum to n sitting on line 6 currently with an n of 2, which is about to be on line 9, and make another recursive call. So we can see the same exact information we saw in the lecture example by running the debugger. So if you want to practice memory diagrams, I would take a piece of code or write a piece of code, or take anything in the examples repo, draw the memory diagram to the best of your knowledge, run the debugger, and see if you can see the same information in the debugger as you drew on your memory diagram. Of course, it's going to be in different format, in debugger format instead of memory diagram format. But you can see all the values in stack frames as you go. We can see that we have 4 frames on the stack, and we can see the values for each one. We separate stack frames in our memory diagrams. The debugger separates stack frames by not even letting you look at 2 of them at the same time. They are completely independent of each other. Okay, this stack frame with n equals 1 makes a recursive call, which is going to hit the base case. I can see all of my stack frames, all the same information. Base case returns. That stack frame is removed from the stack. Well, it's still returning. It returns. We're back in the stack frame where n equals 1, which just got its return value. We don't store the return values in a variable in this example, so we can't quite see what was returned. But if we see the return values all the way up, like we can do the math, I guess. 2 plus 1, this is returning 3, returning 6. And then we can finally see in our main method that result gets the value 6 and prints it to the screen. We're in the debugger tab. If you want to see what's printed to the screen while you're running the debugger, head over to the console tab and we can see that that 6 was printed to the screen. I want to jump back to this example we had that we were running the debugger in last time. This one's a little trickier for the debugger to kind of handle. We put breakpoints inside our conditionals, for example. Put them back in. And I just want to show a few other debugger tricks that I'll start using. When I pull up the debugger, some of these things, I might remind you a few times, but I'll just start using these things. So we did step into. We're stepping into each method call. But if we use this step into, we're eventually going to get into some mess like this. We're in abstract string builder, a method we've never heard of. We got all these frames on the stack. And we have this for each. Whenever you see this for each, this is how Scala executes for loops. It's actually a method call. So it puts another frame on the stack. Don't do that in your memory diagrams, of course. But that's what you're going to see in the debugger. You're going to get into a mess like this, where you're actually deep into the Scala code itself, the Scala language, and the Scala standard library code. Almost certainly not where you want to be. But you will end up getting here often when you're running the debugger. Whenever you get in a mess like this, we want this step out button. Step out is going to resume execution until the current stack frame returns. So we're going to get rid of the current stack frame, and I'm going to keep clicking that until we get back to code that we actually care about, code that you've written, assuming you're debugging your homework code. Once you get back to code that you're actually concerned about, then you can keep going through the execution of this. Another thing, the debugger won't really show you all the variables on the stack when they're not in scope. Variables that aren't in scope, that are in the current stack frame, are not shown. It only shows you the variable with the name that's in scope. So if you're going through that example with the 4 X's on the stack, you're only going to see the one that's currently in scope in the debugger. So I just wanted to note that. And if we have a method call, I'm going to get rid of this breakpoint and hit resume just so I can get to where I want to be. Resume is going to continue execution until you hit another breakpoint. And say I have a method call, I'm about to call reverse. Suppose I have a method call that I don't care about. I have this reverse method and maybe I've tested it I'm comfortable with it. I know that that's going to return the right thing and doing what it's supposed to do. And even if not, I'm still going to see its return value. But I just want that whole thing to run without stepping through it. That's where I'm going to click Step Over. Step Over is going to advance one line, but it will not go into method calls. Step Into will go into the method calls. Step Over, one line, not executing method calls. So if I'm fine with reverse, which, oh yeah, I forgot. Why does it, I don't know why it shows the string in such a crappy way. I got to get out my ASCII chart to realize that that's OG. I'm going to step over, and that's going to skip that entire stack frame for the reverse call, and I should, hopefully result gets its value now. Well, it doesn't. But we can see the ASCII values at least swapped, and now I have go stored in there. So I can still tell my method did the right thing, albeit in this, I don't know why it does that, albeit in this strange way. It's a string. It's treating it like it's a byte array, and I don't know. It's weird. It does it fine right here. I mean, it shows me that information, but it still shows me the toString. But we can skip over method calls. So if there's a method call you don't want to go into, step over. So step over, step into, step out, resume, rerun, and stop. I guess I use this button a bunch too. I'm done. I just want to shut it down without going through the end of the program. Those are the important buttons there. 49, oh man, I didn't think that'd take that much. Let's hop over here. Have a great day. I'll see you Friday.